What's going on, guys? In this video we are going to see the proof of this proposition number 2. Proposition number 2 says any non-empty subset of integers which is bounded above has maximum. Let A belongs to a subset of Z, that's integers, with A is non-empty. If there exists a B belongs to integer such as x is less than or equal to B for all x belongs to A, it means bounded above. This statement states that this is bounded above. Then there exists an A belongs to A where x is less than or equal to A for all x belongs to A. Now let's see how to prove this one. First of all, proof. First of all, let's draw a diagram for this one. We have A right here and we have B right here, and here we have to prove that here we have a maximum A. That's what we want to prove, because it says any non-empty subset of integers which has bounded above has a maximum. If we can prove this one, then we are done with the proof. Okay, now let's go ahead and start the proof. First we are going to let the set is equal to B minus x, and we are going to say x belongs to A. Then B minus x is greater than 0 because it's an integer. B minus x is greater than or equal to 0. Then because if we rearrange this one, this is going to be B is greater than or equal to x for all x belongs to A. Now by well ordering property, if you want to know what is well ordering property, I made a list of well ordering property is one of the axioms. If you want to know all of the axioms that is related to these proof questions, I made a video on that. I put the link of the video in the description, so you can go ahead and watch them. By well ordering property, S has a minimum. Let us assume B minus M is equal to minimum of set M belongs to A. Okay, let's continue here. It means B minus M should be less than or equal to B minus x for all x belongs to A. Now to get rid of this B, we are going to add negative B to both sides. Add negative B to both sides. When we add negative B both sides, this is going to become negative M is less than or equal to negative x. Now if we multiply both sides by -1, the sign flips, so the equation is going to flip around. So M is greater than or equal to x, so for all x belongs to A, and from this one we can see that M is a maximum of A, and therefore we proved this one. Okay, we proved that above has a maximum. Now there's another proof for this. Now let's look at that one. Let's get rid of this first proof. Okay, here now we are going to do the second proof. By second proof, we are going to let the set is equal to minus x belongs to A. Then since A was bounded above, then x is less than or equal to B. Then minus x, the opposite of sign, this will flip around, greater than or equal to minus B. Then we can say S is bounded below by negative B. S is non-empty because A is not empty. Okay, now let's continue here. Then by proposition number 1, if you want to know proposition number 1, I made a video on that previously, so you can watch that too. Proposition number 1, S has a minimum. S has a minimum. Now let us assume that minimum of set is equal to negative m. M belongs to A. This means minus m is less than or equal to minus x for all x belongs to A. M is greater than or equal to x for all x belongs to A. Therefore M is maximum of A. Okay, so we have seen two proof. This is proof number 2, and therefore we proved proposition number 2. I hope this helps. Thanks for watching. And if you are trying to learn discrete mathematics, there are a bunch of videos in my playlist. I hope you guys watch that too, and don't forget to subscribe. See you next time.